previously turned classical problems into quantum mechanical ones by writing a classical equation in terms of momentum and position, and then substituting the momentum operator everywhere we had classical momentum in our classical equations. For example, this is essentially what we did in constructing the Schrödinger equation. This was, of course, just an intelligent guess of what to do. We might hope, though, that by using such a procedure, the quantum mechanical results would correspond well with the classical ones in some kind of classical limit. Of course, the ultimate test of such an approach is that it leads to a quantum mechanical model that agrees with reality. In the case of the Schrödinger equation, that has certainly been the case. So that makes us at least optimistic about this kind of idea. Indeed, it turns out that this kind of approach seems to work quite well in a broad range of situations. And here we can make use of a form of result that was already quite useful in classical mechanics, in what are known as Hamilton's equations. Hamilton's equations are a way of describing classical mechanics in terms of position and momentum. The core idea is that we deduce an expression for the total energy of the system in terms of position and momentum, an expression that is known as the classical Hamiltonian. We then can obtain two differential equations involving that Hamiltonian and the position and momentum. These two differential equations are, of course, Hamilton's equations. As we've described them so far, there's not much apparent reason for taking this approach in classical mechanics. For some simple particle, we're not achieving anything that we could not already achieve quite directly from Newton's laws. However, Hamilton's equations allow a generalization. The quantities in the equations do not have to be simply the position and the momentum of some particle. What we do first is to put together a Hamiltonian function in terms of two quantities, which we could now call effective position and effective momentum, such that both of these differential equations look the same as they did before. Then we can apply the same mathematical techniques to solve for the behavior, just as if we were looking at the actual position and momentum of a simple particle. This kind of approach often allows us to handle much more complicated situations by breaking them up into several problems, each of which can be written just with versions of these Hamilton's equations. Once we've established these effective positions and momenta in some classical situation of interest, we can then try to quantize the situation simply by substituting a corresponding effective momentum operator for the effective classical momentum. In classical mechanics, we can write a function which we call the Hamiltonian that represents the total energy. And in the case of a particle in one dimension, it's just a function of the momentum, p, and the position. And here we use q to represent position. P and q are considered to be independent variables in this description. Hence, in classical mechanics, our classical Hamiltonian, which is just a function, is p squared over 2m plus v of q, where v of q is just the potential energy, the function of position, q. The force on the particle is just the negative of the gradient of the potential. That is, a particle accelerates when it's going downhill. So the force on the particle is the negative of the gradient of the potential because downhill is a negative gradient. So, with the Hamiltonian just being p squared over 2m plus v of q, the force, which is minus dv by dq, the negative of the gradient of the potential, is therefore minus partial dh by dq. If we look at the Hamiltonian here and take the partial derivative of the Hamiltonian with respect to q, we simply get minus the force. So the force is minus dh by dq. As usual from Newton's second law, force is the rate of change of momentum. So rate of change of momentum, of course, is dp by dt, and that therefore is equal to minus partial dh by dq. Again, with our classical Hamiltonian, p squared over 2m plus v of q, we also know that the partial derivative of the Hamiltonian with respect to p is just p over m. That's the derivative of this term. This term does not depend on p. So, since p is equal to mass times velocity in classical mechanics, and by definition velocity is the rate of change of position, then we have that the rate of change of position is dh by dp, because p over m is just velocity. These two equations, dp by dt is equal to minus partial dh by dq, and dq by dt is equal to partial dh by dp, are known as Hamilton's equations. If the Hamiltonian depends on two quantities p and q, and these quantities and the Hamiltonian obey Hamilton's equations, then we have found the quantities analogous to momentum and position. It has been very successful in quantum mechanics to start with a classical version of the problem with a Hamiltonian and quantities p and q, all obeying Hamilton's equations, and then to propose a quantum version by substituting a differential operator minus ih bar d by dq everywhere in our classical expression we find p. In this use of the Hamiltonian and Hamilton's equations, both in classical and quantum mechanics, the quantities p and q may bear little direct relation to the momentum or position of anything. All that matters is that the Hamiltonian should be a function of p and q that correctly represents the total energy. And the Hamiltonian and the variables p and q should obey Hamilton's equations. Up to this point, our description has been rather abstract, and we will not be able to take the time here to go through the use of this approach in classical mechanics in general. However, in the next section, we will look at the classical Hamiltonian of the electromagnetic field in this kind of form. That concrete example will make this approach much easier to understand.